Alright, hello everyone. So, last video we tried finding the solution for a second order linear homogeneous differential equation with constant coefficients. We saw that we consider y equals e to the power mx as a solution. If we just tried it out, and in fact, we saw that given that we can find solutions to this quadratic equation, which we always can, okay, we will have y equals e to the power mx will in fact be a solution to the differential equation, okay. And we also use the fact that we have two solutions to the quadratic, okay, two different numbers, two numbers at least. That's what I'll say for now. So we have two numbers, and so we'll have two solutions. We should have two solutions. If you have two solutions and this is a homogeneous equation, linear homogeneous equation, we already saw before that we can take a linear combination of those two solutions. Okay, we can take a linear combination of them, and that will also be a solution to my differential equation. So this is the general solution because we are making up for those two arbitrary constants. This has two arbitrary constants, which it should to be the general solution of a second order differential equation. So that is why this is the general solution for my differential equation. All right. So as I said, what we need to do, we're given any second order differential equations. First, write the characteristic equation. Write this characteristic equation. Just replace the derivatives y and all by the corresponding powers of m and all. Okay. So and then we should be able to find solutions to our differential equation. Now, as I said in the last video, we have three different cases. We have three different cases for the types of solutions to a quadratic, right? Okay, and the first one that I'll talk about in this video is two distinct or unique, two distinct. Actually, unique, two unique slash distinct real solutions. Okay, two distinct or unique real solutions. Okay, so what happens if you have two different real numbers as solutions to my characteristic equation? That's actually the simplest case. That's actually the simplest case. And to illustrate that, I'll just solve a problem right now. So suppose say you have the differential equation, y double prime minus 5 y prime plus 6 equals 0. Now, as I said, to find the solution to my differential equation, first I'll need to write down my characteristic equation. For that, I just need to replace all the, wait, not 6. I'm sorry, I'm really sorry about that. Should be 6y. Should be 6y right here. Okay, so all that we need to do is replace the derivatives y and y by the corresponding powers of m, okay, which is basically our constant, or the thing we need to solve for in our characteristic equation. So y double prime, it's gonna be replaced by m squared, second derivative squared. Okay, so then we have y, 5 minus 5 multiplied by y prime, so that's m to the power 1, or just m, okay, plus 6, okay, plus 6 multiplied by just y. Again, y is the zeroth derivative, that's why we replace by m to the power 0. And so m to the power 0 is just 1, right? Okay, that's why we don't need to write anything here. Just 6 multiplied by 1, that's just 6. Don't need to put anything for y right here. So this is my characteristic equation. This is my, I'll again emphasize and write that down, but this is my characteristic equation. So I'll actually write that in short. So now we just need to solve for this. It's actually pretty easy to solve. We can factor this. So if we do that, what we'll get, the two factors are gonna be, let's see, m minus 3, and m minus 2. Yeah, that looks good. Product is plus 6, and we get minus 5 in the middle. That looks good. So m minus 3 multiplied by m minus 2. That's factorization, and this is gonna equal 0. So our solutions are m is gonna equal 2, or m is gonna equal 3. So there are two solutions, 2 and 3. Now this is actually the case that I want to talk about when you have two distinct real solutions, And okay, so as I said, if we have two solutions, what our we this should be our general solution, right? This should be our general solution to my differential equation. Now, this will in fact, as you can see, if we just plug in those numbers, let's try plugging those two numbers that we got, for m1 and m2. So, suppose say, this we could consider as m1, okay, this is two. Now our solution is our general solution to my differential equation. This is fascinating. It's the first time we're actually doing this. It's gonna equal some arbitrary constant c1, okay, e to the power, one of these, so 2x, okay, m1x plus c2, okay, multiplied by e to the power the other one, so 3x. And so, is anything wrong here? Is anything wrong? And actually, the main thing about these three different cases is we just need to see if the way we write the solution at the end, if there's something wrong with it. And I'll explain more of that later. So, no, it doesn't seem like there's anything wrong. Nothing weird going on here. This does seem like a valid solution, and this is in fact our general solution. This is in fact our general solution. And the more importantly, what I want to say is, this is how you find the general solution, okay? When you have two distinct real solutions for your characteristic equation. When your characteristic equation yields two distinct real numbers, okay? If you want to generalize that, you could say, when if this was your characteristic equation, if b squared minus 4ac, if your determinant b squared minus 4ac is greater than 0, minus 4ac is greater than 0, then all that you need to do is solve for your characteristic equation. Solve. You'll get two values, and then you just plug them in, and you'll get your general solution. That's pretty fascinating, and it's the simplest one, actually. It's the simplest one out of the three cases, as we'll see. So let's actually do some more practice with this. First thing is, actually, with this equation, I'd like to tack on some initial conditions. As I've already told you, we need two of them. So let's say that we have this differential equation, and also the fact that when x equals 0, y is gonna be 2. Okay, y is gonna be 2, and also y prime of 0, okay, is gonna be, let's see, it's gonna be 5. It's gonna be 5. All right. So let's actually try to find a particular solution to my differential equation, since we now have initial conditions, as we can see. So first thing, was what we see is, okay, so x equals 0, y is gonna be equal to 2. So let's plug those in. Let's see, x equals 0, this is just equal to 1. If this is equal to 1, this is equal to 1, and what we'll have on the left side is 2. Okay, 2. So our first simultaneous equation, which says 2 equals c1 plus c2, c1 multiplied by 1 plus c2 multiplied by 1. Anyway, so that's one equation. So it's not enough for us to solve for c1 and c2. We also have another piece of information. When x equals 0, the first derivative of y is gonna be equal to 5. Okay. So, but before that, and again, this is also something that we're doing maybe I guess for the first time. Not too sure about that. But anyways, to actually use that, first we'll need to find the first derivative, right? Actually, I think I did this in the something like this in the second video. But anyways, we first need to find an expression for this first derivative, right? Let's do that. If our general solution y is this, so our the derivative of that is gonna be y prime is gonna be, so if you differentiate e to the power 2x, you get 2 e to the power 2x, and so what you'll get here is 2c1 e to the power 2x. Similarly, with the other one, what you'll get, 3 comes out, and what you'll get is 3c2 e to the power 3x. All right. So, and what we have is, what we said is, when x equals 0, this is gonna be equal to 5. Y prime is gonna be equal to 5. So left side is 5, the right side is, this is again, this is, when x equals 0, this is gonna be 1, this is gonna be 1. So what we'll have here is 2c1, okay, multiplied by 1, okay, plus 3c2, again multiplied by 1. So this is another equation. So we have two equations. I actually should have wrote that here. So I'll actually do that. So we have 2 equals c1 plus c2, 5 equals 2c1 plus 2c2. Okay, I'll call this equation 1. I'll call this equation 2. And so we can actually, we could do this by hand. We could use the calculator to solve this. Let's for now just actually do this by hand. So what, if we actually, why did I write 2 here? It's 3. Okay. So if we do that, let's actually, use elimination. Equation 1, you can write this, if you multiply all sides by 2, you'll have 4 here, 2c1 here, 2c2 here. Subtract, your equation 1 from your equation 2. What you'll have is, 5 minus 4 is 1, okay, is 1. You'll have 2c1 minus 2c1. That's exactly what I intended, this to cancel out. 3c2 minus c2, just have c2. So c2 is equal to 1. And if you substitute that here, you'll also get, c1 being equal to 1. c1 will also equal 1. So that's interesting. c1 and c2 are both equal to 1. And now we have solved for both our arbitrary constants. They're arbitrary no more. So our particular solution to my given differential equation, given those initial conditions, is y is equal to c1 is 1, so just e to the power 2x, and c2 is also 1, so again just e to the power 3x. So this is my particular solution. Okay, so pretty interesting, pretty fascinating. Let's actually just try to find the general solution to one more problem. Just some practice. Our equation is y double prime plus y, actually minus y minus 1 is equal to 0. Our characteristic equation is just going to be y double prime, replace that with m squared, minus y, replace that with m, and minus 1, don't need to replace that with anything, and this is going to equal 0. And our solutions are going to be, doesn't look like we can factor this, so our solution will actually rely on the quadratic formula. Negative b, negative of negative 1, that's 1 plus or minus b squared, so negative 1 squared, that's just 1, minus 4 into this, so 4 into 1 into minus 1, so that's plus 4, right? Divided by 2 multiplied by 1, 2 multiplied by 1. So this is gonna be equal to, let's see, 1 plus or minus 1 plus or minus, let's see, root 5, square root of 5 divided by 2. And okay, for those of you who are just can notice this or a bit curious about this, if you take the positive version, that's actually your golden ratio. Anyways, that's not really the topic here. Now all that we need to do to find the general solution is plug those numbers in into our this general solution equation that we have. Okay, so what we're gonna have, our general solution is gonna be c1, some arbitrary constant c1 multiplied by one of our solutions. So I'll take the positive version right now. 1 plus root 5 divided by 2, that's multiplied by x, plus c2. Okay, we have c2 multiplied by e to the power 1 minus 1 minus root 5 divided by 2 multiplied by x. Again, the main reason I did this problem is, one thing, we'll sometimes have to use the quadratic formula. Another thing, no matter how not so neat the real solutions look, as long as you have real solutions, the process is always the same. Okay, the process is always the same. You just solve your characteristic equation and plug the solutions in here, and you'll get your general solution. Okay, then if you have some initial or boundary conditions, you can find your particular solution. All right, so I think that should be enough to cover this one case. The next two cases will be dealt with the next two videos. So That's the end for this video. If you like the video, please do leave a like. If you and subscribe and keep studying smart. And yeah, see you later.